Hello, everyone. My name is Aleksandr. I'm a postdoctoral researcher based in Stockholm, and my work focuses on understanding dynamical processes in the early universe and predicting their observational signatures. And it's my pleasure to present my work at Early Universe from Home. And today I will talk about string-induced vacuum decay and its gravitational wave signatures. And this work was done in collaboration with Florian Niedermann and Phoebe Richman-Taylor. So cosmological observations are entering precision era and becoming increasingly powerful probes of particle physics. A particularly remarkable breakthrough has occurred in gravitational wave astronomy over the past decade. And this includes the first detection of gravitational waves by laser interferometers in 2015, as well as the currently strong evidence for low-frequency gravitational waves observed by pulsar timing arrays, which appears as correlated timing delays in pulsar signals with a very characteristic angular pattern. So in the interferometer case, the origin of the signal is clearly astrophysical. For the pulsar timing arrays, however, the origin is less certain. It could arise from merger of supermassive black holes in the center of galaxies, but cosmological origin still remains a compelling possibility. And it is important to remind ourselves that gravitational waves can probe epochs far before CMB, and thus they provide a unique window into the early universe. And there are several possible cosmological sources of strong gravitational waves, and in this talk I will focus on actually two of them simultaneously, namely first-order phase transitions and topological defects, in particular cosmic strings. The outline of this talk is as follows. In the first part, I will focus on the theoretical framework. So I will introduce the idea of string-induced vacuum decay and explain how bubble nucleation on top of cosmic strings can be studied in the thin wall limit. And in the second part, I will discuss phenomenological implications of this scenario, and I will focus on two gravitational wave signatures, gravitational waves from non-spherical bubbles and gravitational waves from metastable string network. And in particular, I will show how nanograph signal can be linked to a phase transition occurring at temperatures around 100 electron volt, so corresponding to a very late time post the BBN phase transition. So let me say a few words about phase transitions. As we know, during cosmic evolution, fields can become trapped in false vacua, and the transition to the true vacuum then proceeds via nucleation of true vacuum bubbles from fluctuations. These bubbles expand and eventually they fill the volume as shown in this picture. And in the standard zero temperature picture, which was derived by Coleman, the fluctuations are of quantum origin, and the decay of the false vacuum is described by the so-called bounce solution, which has a Lorentz symmetry, or in Euclidean time, O4 symmetry. And nucleation is statistically homogeneous in position space. Now, at finite temperature, thermal fluctuations become important, and Lorentz symmetry is no longer present. However, the bounce still maintains its spherical symmetry. The situation changes when the background contains inhomogeneities. In this case, nucleation may predominantly occur around these inhomogeneities, and bubbles no longer have to be spherical, and also the decay rate can be significantly modified. A particularly important example of such inhomogeneities are topological defects, such as domain walls, strings, and monopoles. This arises whenever the theory has non-trivial vacuum manifold, and they are produced during symmetry breaking, and also they are protected by topology, which makes them very stable. And the role of topological defects for phase transitions was first studied by Steinhardt back in the 80s. And in this work, I will focus mainly on cosmic strings, which arise whenever the potential has this type of Mexican head shape. So let's discuss the minimal setup that we need here. It's a complex scalar field charged under U1 symmetry, either global or local. However, importantly, in our case, we require the potential to have two local minima. A false minimum at the symmetry breaking value, and the true minimum at the origin. And this type of potential is shown as the solid black curve in this plot, and it's compared to a more usual Mexican head potential, which is shown as this dashed line. So As it's well known, such potentials support global and local cosmic strings. And for simplicity, we can consider a straight string aligned along the z-axis, and in that case, the field profile, the field profile has the following form with the winding around the string core, and the radial profile at large distances approaches the false vacuum, whereas in the core of the string, it sits at the origin. The crucial point here is that for the black curve, for these type of potentials, with the true vacuum at the origin, the strings are no longer absolutely stable. And this can be understood intuitively by noting that if the core of the string expands sufficiently, then the system gains a lot of negative energy from this vacuum energy difference. And hence, such strings can at most be metastable. To gain further insight, it's convenient to use the thin wall approximation. In this limit, the string profile can be separated into three regions: an interior where the field sits at the origin, an exterior where the field sits at the false vacuum, and a thin wall separating the two. And in the thin wall limit, the width of the wall is much smaller than the radius of a string. And this approximation is valid whenever the energy difference between the two true and the false vacua is much smaller than the height of the potential barrier separating them. And essentially, in this case, we can make the following ansatz and effectively integrate out the radial variable. And then the bounce is described, the string profile is characterized in terms of one variable, capital R, the string radius. Having said that, the radius of the string is then determined by computing the energy per length of the string and as a function of R, which has the following form. And one finds that for a certain range of the parameter which we define as x, which is given by the following expression, the energy function indeed has a local minimum. And this local minimum essentially corresponds to a metastable cosmic string configuration. And indeed, you can see the metastability from the fact that for very large values of the radius, the energy goes down. For values of x larger than 1, there is no local minimum, and in this case, the string becomes classically unstable. The radius of the stable string is given by the following expression. Now, to describe the false vacuum decay, we need to compute the bounds, which is a classical solution of the Euclidean equations of motion with particular boundary conditions, such that at large distances, the configuration approaches the false vacuum solution. In the absence of strings, so for homogeneous vacuum, the bounce has a O4 symmetry and can be parameterized in terms of this variable rho, which is given by the following expression. And now, in the presence of a straight cosmic string, this symmetry is obviously reduced. However, it has been shown by Dasgupta for the first time that there exists solutions which respect O2 times O2 symmetry. Here, one of these O2s corresponds to rotations in XY plane, so inherited from the string, and the other O2 corresponds to rotation in the Z and Euclidean time plane. And this reduction of symmetry is illustrated in this plot, where now instead of the O4 symmetric bound solution, we have this O2 cross O2 solution, which at large distances indeed reduces to the string solution. And in this work, we only consider vacuum tunneling. That's why we deal with this O4 and O2 cross O2 symmetries. Now, again, computing the full bound solution numerically in the presence of strings is quite challenging. And instead, in the thin wall approximation, this is more easy because then the bounce is parameterized by a single function, this capital R, which is now not a variable, but it's a function of this new variable rho. And we carefully derived the Euclidean action, and we included here some relativistic gamma factors, which were missing in earlier treatments, and which I will refer here as non-relativistic treatments. And yeah, essentially in this limit, the problem reduces to one-dimensional tunneling in quantum mechanics, which can be solved by standard shooting methods. And the resulting bounce profiles are shown in this plot as the solid curves of different colors corresponding to different values of x. Again, here for simplicity, this is shown for the case of global strings, but we have done the analysis also for local strings. And you can see that for small values of x, when the string becomes very small, the bound solution essentially recovers the O4 solution. Whereas for large values of x, the bounds is very non-spherical. And the dotted lines correspond to the analytic continuation of these solutions to real time. Finally, we computed the bounds action, which determines the leading contribution to the exponential to the decay rate. And here we show the bounds action in units of the bounds, or O4 bounds, as a function of the x variable for the case of global strings. This is the black solid curve. And for the local strings, it's the blue curve, which now depends, instead of x, on a y variable, which has a different form, but plays a similar role. And yeah, we find that as you can see, the bounds action is always smaller compared to the O4 case, meaning that the decay rate at this order is enhanced. And the dotted curve here corresponds to the non-relativistic approximation, which I mentioned before. And as you can see, there are noticeable deviations from it, especially at small values of x. Okay, now if we include also the prefactor in the decay rate, we find that the string-induced channel is more efficient than the homogeneous one only if the parameters x or y are in the following range. So in other words, if they are roughly order 1. And the reason is the following. The string-induced bubble nucleation can occur only on top of the string, while the spherical bubble nucleation can occur anywhere in the bulk. And for small values of x or y, this geometric suppression becomes more important than the modest reduction of the bounds action. And to reach this conclusion, we of course compared the percolation times of these two channels, assuming on average one Hubble-sized string per Hubble patch. We have discussed the enhancement of the decay rate. Let me now turn to the gravitational wave signatures of this process. So gravitational waves are sourced by time-dependent quadrupole moments, as indicated by this formula, where this is the definition of the quadrupole moment. And so in the standard picture of first-order phase transitions, individual bubbles are assumed to be spherically symmetric. And such configurations have vanishing quadrupole moment, and as a result, the dominant contribution to the gravitational radiation comes from bubble collisions, which obviously break the spherical symmetry. In contrast, in the string-induced scenario, the bubbles are elongated along the string, and as a result, they carry non-vanishing quadrupole moment, which means that even individual expanding bubbles already source gravitational waves. And in this work, we compare these two contributions. So to do this, we note that for both mechanisms, the typical frequency of the emitted gravitational radiation is approximately set by the inverse lifetime of the source, or in other words, the inverse duration of the phase transition. So what remains to compare is the strength of the radiation, which in turn is determined by the quadrupole moment. So for the collision of bubbles of radius r, the quadrupole moment can be very naively estimated as this, r to the 5 times delta v. Whereas for non-spherical bubbles, in our scenario, we compute their quadrupole moment directly from our numerical solutions and their analytical continuations. And the ratio of these two contributions, the ratio of the second contribution to the first one is shown in this plot as a function of the bubble radius as the bubbles expand. And for simplicity, in this figure, we consider the global case, but for the local case, the behavior is the same. And these three different colors are, again, three different benchmark parameter values. So as we can see, as the bubble grows, the ratio decreases, and this reflects the fact that the bubbles become more and more spherical as they expand. Therefore, if the bubbles expand significantly before they collide, we expect that the radiation from individual bubbles is going to be subdominant compared to this collisional contribution. Next, we consider gravitational radiation from the strings themselves. And so as it was already mentioned, string networks are formed during spontaneous symmetry breaking. And as the network evolves, strings intersect, intercommute, and form closed loops, which oscillate and emit gravitational waves. And for stable strings, these loops are continuously produced until today, resulting in a very flat gravitational wave background spanning wider range of frequencies. It's given by the following expression, where μs here is the string tension and n loop is the number density of loops of a given length at time t. In the metastable case, the situation changes. In particular, the string network disappears after the phase transition, and as a result, the gravitational wave spectrum is suppressed at small frequencies. And this has important implications for pulsar timing array observations. So metastable strings not only provide a better fit to the PTA data for gravitational waves, but they also significantly weaken the bounds on the string tension. And this is similar in spirit to the more conventional metastable string scenario in which the strings decay by producing monopole-antimonopole pairs. Here we illustrate this in more detail. In the left panel, you can see the spectra of gravitational waves from stable and metastable string networks for various values of the transition temperature and the benchmark value of the string tension. And the spectra are compared to the nanograph 15-year data. So as can be seen, the slope helps to fit the data better. In the right panel, you can see a frequentist analysis of the parameter space of this model, where in the x-axis is the string tension and on the y-axis is the transition temperature, and the blue contours correspond to 1 and 2 sigma intervals. So everything above these contours is not constrained by PTAs. And there are additional constraints on cosmic strings coming from LIGO, which excludes strings with tensions 10 to the minus 6 or above. And so this benchmark point 10 to the minus 7, which is also inspired by theories of grand unification, is safe from constraints, from bounds. And this yellow and orange points correspond to these curves in the left panel. And interestingly, as you can see, the corresponding interesting range of temperatures of the phase transition is post-BBN and prior to recombination temperatures. So we are dealing with a late time phase transition here. We also constructed a simple two-field model that describes both the formation of the strings and their eventual decay. And the second field, chi, controls the shape of the potential. And the idea is that initially the field is at this red point, where the phi equals 0 is a maximum. So the potential is really a Mexican head potential, which allows the formation of a string network during symmetry breaking. Then the chi direction is very flat, and so it's only at later times that does the system evolve toward the new minimum at this green point. And here the strings become metastable, and because now there is a true vacuum at phi equals 0, and this channel of string-induced vacuum decay is now active, leading to delayed symmetry restoration and bringing the system to this blue point. Okay, let me conclude with some final remarks. So we studied false vacuum decay catalyzed by cosmic strings and discussed its gravitational wave signatures. We found that the PTA signal can be consistently linked to symmetry restoring phase transition occurring after BBN. In the simplest case, of course, in the dark sector. And let me also mention that such late time phase transitions are also interesting in the context of the Hubble tension. Because in particular, the energy injection from the latent heat of such transition, if it's around 10%, it resembles the mechanism behind the new early dark energy models addressing the Hubble tension. And this deserves further investigation. And with this, I would like to thank everyone for your attention. and looking forward for discussion during this conference.